My name is Łukasz Langa. Today we're going to talk about FM audio synthesis, and in particular about real-time FM audio synthesis in Python. You might know me for releasing Python for you or for creating the black code formatter, but I'm also pretty invested in the music industry. In fact, I'm collaborating with Poly and a Polish company on a bunch of their devices right now. This one that you see on the picture is Medusa. That's a hybrid synthesizer, meaning it combines both analog and digital synthesis. And in particular, I was contracted to add digital FM synthesis to that device. Bear in mind, this re-implementation is in C++, but the concepts that we're going to be discussing are pretty much exactly the same. It all started in 1983 when one of the best-selling synthesizers in history was released, the Yamaha DX7. It was based on John Chowning's research at Stanford University on frequency modulation. It's been pretty cheap, so it's been widely used in 1980s music, from Michael Jackson, Aha, Whitney Houston, Phil Collins, Enya, Sting, essentially you name it. It's been the sound of the 80s. But even across the 90s up to today, it's being widely used by many bands for some of the sounds that are very unique to this instrument. It's known to be used by Depeche Mode, The Cure, and Nine Inch Nails, in fact. Like the picture that you're seeing here is from a Hard Rock Cafe in Wrocław, where I took it. Let's hear how that particular code that we're going to be writing today actually can sound. Like this will probably allow you to be a little more patient with whatever we have to do to actually make the code work. So here it is. This is how the end result sounds. Back to our code. So signal flow that we're going to be using is going to be as follows. Python is going to be listening to musicians' notes being played on a MIDI controller. It's going to synthesize sound in real time, and using the mini audio library is going to take this raw data, there's going to be a bunch of integer arrays, and send it to an output device. This output device could be any sound card, in fact, or an audio interface as they're called in the industry. But we're going to be using Blackhole, which is a piece of software. It's a virtual audio driver that acts as a virtual output device. This allows us to route signal from our Python code to an actual audio workstation. And we're going to be using Ableton Live for this purpose. This allows Ableton Live to take data from Blackhole as input, and we can then record it, apply effects to it, multi-track it, mix it. This actually makes it industry grade. All right, so Mini Audio is a pretty cute single file library that allows for cross-platform audio playback, and this is exactly what we're going to be using it for today. And it's got very good CFFI bindings for Python, so we're going to be using those as well. Blackhole is macOS specific, but if you have Windows, there is an equivalent virtual audio driver, and on Linux, I believe Pulse Audio has this functionality built in. So that's Ableton Live, our digital audio workstation of choice for today. We can see an audio track here and a MIDI track. We're going to be using both today. To actually make it all work, we need to tell Ableton Live to treat Blackhole as our audio input device today. And this allows us now to just select any of its external inputs and record it or just monitor them, so meaning listening to them, this sort of thing. So we're going to be using that. So those are our components, right? Python, Mini Audio, Blackhole, and Ableton Live. Let's start filling in the Python part. But before you get all nervous about not being able to follow along, don't worry, all of this is on GitHub. You can pretty much just clone it and look at it at your own convenience. The commits in that particular demo repository are roughly in the order that we are doing things today. So you can just check out a particular commit to see the state of the code at that particular moment in time. I hope they are described clearly enough. So let's start by looking at what audio devices my computer even has. Let's use bpython as the REPL and enrich to pre-print built-in data structures. So now we're importing devices from Mini Audio, which allows us to enumerate them, and in particular to enumerate the ones that allow playback. There's a bunch of them here, including useless ones like the one in my display or the one in my Thunderbolt dock. But the one that is important is this black hole one. We're going to be using this one. As you can see, comparing with the MacBook Pro speakers below, it doesn't actually look any different. So this is sort of the point, that now it doesn't matter whether we're sending signals straight to some physical output or to black hole to route it to Ableton Live or any other digital audio workstation. So our code uses the same functionality to enumerate over all devices, choose the one with a matching name, and build a playback device object from it. With that, we can stream some audio. Let's say we're going to be streaming some cowbell sound, okay? Note that the playback device that we have here, produced on line 29, is used as a context manager, and streaming happens in fact in a background thread. So for now, we need to use time.sleep to ensure the application doesn't finish before the sound finished playing. So let's run it. Beautiful, a classic Roland 808 cowbell sound. That's the same sound in Ableton Live. Let's add some reverb. Cool. Maybe some delay. All right, nice. This shows why using a digital audio workstation is so powerful. But we don't want to just play samples. We want to synthesize our own sound. To do this, we'll use low-level numeric arrays, 16-bit signed integer arrays to be exact, as this is very popular for audio. I already prepared a function that generates a single cycle of a sine wave of a given sample length. That single cycle is very, very short. So now let's make a generator that will loop over this single cycle forever to produce actual sound. For this, we're already using the API of Mini Audio, which likes to use generators for everything, but they're very specific generators, meaning Mini Audio will send to the generator information about how many frames it wants us to send back. So this is essentially what we're going to be doing right now. There are loops that are just putting the right amount of frames in an array object and yielding it back, asking for how many more frames does Mini Audio want from us. So there's essentially very little complication here. The only thing we need to remember is what index we finished at and to loop over when we reach the end of the sample. So now we can replace our cowbell with a stream of our endless sine. The one weird thing that we need to do is to have a single pull from the generator first before we pass it to Mini Audio. Why is that? Well, looking at our generator function, we see that there's some setup before the first yield. So before the first value is received from external controllers, callers of the generator, there is already some code that is running. And this is the code that we're running by running this first bare next. If we tried to already pass a value during this first next by just using .send, Python would not be very happy with us because you cannot really send values yet when a generator is not running yet. So now you might be wondering why we're even yielding full arrays of values. We might have just as well just yielded single values. That would make everything much simpler. And you'd be correct. but it would also overwhelm Python. Generating sound in chunks is a very smart compromise here. So let's hear our endless sine. Nice. Let's add some reverb. Cool. Sounds fuller. And now some delay. All right, pretty good. 100 samples at 44.1 kilohertz is very close to 440 hertz, the standard pitch of A4. If we asked for a longer sine wave, it would produce lower notes. If we generated a shorter sine wave, it would produce higher notes. So let's see our sound on a spectrogram. While the scale here is logarithmic, we can see that it's 440 hertz indeed. But wait, what are those unhappy pops at the start and here at the end? Let's look at our samples in time. So at the start of the sound, the upward slope starts pretty aggressively. If I insert some silence at the beginning, this is easier to see. The sharp angle here causes a pop. It's not a particularly bad pop, but it's there. At the end of the sound though, the situation is more severe. We don't actually end the sound exactly at the end of the full cycle. So this sharp angle here produces an even louder pop. Ideally, we'd like our sound to decay gently, and on the attack side also have a short while to get to full volume. That way you avoid those sorts of clicks and pops. We can achieve this by using an amplitude envelope. The way we will use this is we will wrap our endless sine stream with a new envelope function, which is also a generator, that also takes an envelope object, which is essentially an object to calculate us the current state of the envelope. We could almost use just a single generator for this, but we need to be able to reset it to play another sound. Before we look at it, a small detail. I added an audio type alias, which is going to be very useful for our program. It's going to be very popular here as a type. So now, onto the envelope object. Looks like a lot of lines, but in truth, it's only a single function that advances the envelope by a single sample and returns its current value. The envelope that we're using here is an attack decay envelope, meaning it takes some time for it to raise to full volume, and then it takes some time to get back to zero. It's a linear envelope. So by setting the samples advanced back to zero, we can restart the envelope. That's going to be useful later. The envelope generator right here contains the same boilerplate setup as we've already seen. And the meat is the loop on lines 62 and 63, where we apply the envelope's current value to the incoming data. So how does this sound? Nice, add some reverb. Same deal, and some delay. Nice, so this is just an enveloped sine, but it's already quite musical, have you noticed? So thanks to mini audio working in a background thread, we can replace this useless time sleep with an async IO event loop to handle incoming MIDI data. Today, we don't have time to talk about how that part works, but fortunately I gave a sister talk to this one at PyCon US last year that focuses exclusively on this subject. The important thing for us is that a MIDI controller will send us note-on messages handled by the method on line 116. And that will allow the synthesizer to play a given note at a given volume. We want to be able to play multiple notes at once, so I made a voice object that combines the previous endless sine logic with the envelope function. Its biggest difference compared to the previous state is that now we can actually change the pitch of the played waveform using that same array. We don't recreate the array all the time. That happens on line 109 and 110. So we're hopping every w_i indexes of our waveform to achieve higher pitches. Now, that's interesting. How does that work? Instead of playing every sample in the array that we have, we're hopping over a few. In effect, the sound has higher pitch. The more indexes we hop over, the higher the pitch. Now, you might have noticed that in this example, every second hop finds itself in the middle between two samples, right? What to do in this case? Well, for the purpose of this talk, we're simply choosing the nearest neighbor index, but for higher fidelity audio, you'd want to consult the sampling theorem and choose a more fancy interpolation method. The one that we're going to be using today causes some aliasing, meaning essentially noise. Coming back to our code, we also introduce a high-level synthesizer object that can hold a bunch of voices, meaning now our synthesizer is going to be polyphonic. It's going to play many sounds at the same time. So the synthesizer object selects one to play when a note on message is received. You can see its own note on message on line 70. And it's doing this very important job to sum output of all the voices it contains into a single mixed down output signal. The mixdown used here is the most basic one. We turn down the volume of each voice by enough so that there's no distortion even if all of them play simultaneously. This is how a MIDI sequence in Ableton Live of our synthesizer sounds. In fact, thanks to how all of this connects together, we are able to not only play this instrument live, but to use a digital audio workstation to synthesize, well, to sequence melodies for us, as I've done right now. But the most important thing is that's pretty pleasant to the ear already, right? And this is only a sine wave that we've synthesized for now. But it's already real time, it's high fidelity, and it's in pure Python. So let's make it frequency modulated. Let's look at the example of sample pitching again. Even though our sine wave table has some air quotes natural pitch, we can pitch it up by hopping through many indexes in a table. And this hopping results in waveform cycles of higher frequency, right? Because we're choosing fewer indexes and putting them out. In other words, there is a way to calculate how many indexes we should be hopping over to achieve any pitch we want. Now, if our hopping changes over time, if the rate of hopping, I guess, changes over time, so will the frequency of the resulting waveform. If that change over time is done in a controlled manner, as you can see in the example, clearly there's some pattern here, we call that modulation, frequency modulation, and voila. This is how the end result looks like graphed out. Let me just kill myself here. If our raw blue signal is frequency modulated with another sign, the orange one, the end result in green ends up being a pretty complex waveform, producing very interesting timbres. Now we can make those timbres even more interesting if we apply amplitude enveloping. So here we envelope the carrier signal with some attack and a longish decay, and you can already see that this essentially appears in the end result. But we can also apply enveloping to the modulator signal, decreasing the amount of frequency modulation over time in this example. It's an important insight to realize that there is no difference between the carry signal and the modulator signal. Their role is assumed only when the two are connected. So for example, I can reverse them. If I reverse the role of the carrier and modulation in this graph, we will get this. Cool. Now, the fun begins when you realize that there is nothing stopping us from using frequency modulation on a modulator, and that now this modulator will further modulate something else. And this is the basis of commercial FM synthesis as we know it. For example, Medusa supports 5 such combinations. Choning came up with the term operator for each of those pitched sine waves that have an attached envelope generator. In particular, when an operator is at the end of the chain and it produces sound, it's called a carrier, as we've seen in the graphs. And if it modulates another operator, it's called a modulator. So Choning called the combinations of the operators algorithms. Now, there's another synthesizer that is very popular these days in FM synthesis called Korg Op6. This one uses 6 operators per algorithm, which allows for way more combinations. Note that some of those even have a loop around them, meaning they can feed their own signal back to themselves. And that feedback actually produces pretty nice FM distorted sounds. But 3 operators are less CPU intensive and easier to demonstrate for now, so we'll focus on that for this talk. So we are going to be renaming our voice into operator, since this is the terminology as we've learned. And more importantly, we're going to be refactoring our output that now is a single non-modulated output into a version that actually listens to external modulation and applies it to itself. So I changed the result, the return type, to FM audio. That only means that it accepts now an entire array being sent to the generator instead of just how many frames do we want. The reason why we accept an array of audio is that now we are in fact using it to modulate our own signal. The magic happens in line 114, where we use the mod underscore scaled variable to affect our index hopping, and that variable comes from the external input. So now the operator is fully functional. We can move on to the synthesizer object. It is not using the voice object anymore. We don't have those anymore. It is using a new one called phase modulator. Phase modulators are going to be the objects that combine several operators using an algorithm into some complex sound. So let's see that phase modulator right now. The phase modulator is another pretty simple data class in terms of its shape, but it has those 3 operators that we've seen and 3 rates. What are those rates? It's mostly musical when the frequencies of our 3 operators still have some relation between them. If they would just be random frequencies that, whenever we choose another note to play, they don't really have, logical relationship, they would, sound dissonant. So to have consonants, to have like nice sounds there, we use rates that allow us to build complex timbres that are still very musical. So here on this screen, we only see how all of this is being set up when you create a new phase modulator object. The note on now actually has to play all of the operators, but the money shot is here, that the most complex output generator of all. But it's not very complex. In fact, it only takes so long because we have 3 operators to initialize, and we have our 5 algorithms that we implemented. And let's see if they are readable. If we look at line 179, we see that the first algorithm, what it does is it takes the output from the 3rd operator, puts it in operator 2. And in turn, it takes the output of operator 2 and puts it in operator 1. And operator 1 is our output, it's our carrier for now. So that's in fact this chain that we've seen, that is a very typical FM algorithm. That pretty much reads as what it does. Like, I find that tremendously readable. Let's try another one. So for example, this algorithm 2 has output of operator 3 being applied to both operator 2 and operator 1. And now, since both of them are carriers, we have to mix them together to yield our output. Pretty cool, right? So that is essentially what phase modulation, what our frequency modulation does. And we can now see how this sounds on the sequence that we've already heard on simple sine waves. Cool. So as you can see, the difference in code is maybe 100 lines, but the result sounds much more rich. This one patch in particular is a very typical 80s power ballad glass electric piano, but there are very many sounds you can accomplish with this synthesizer engine. In fact, if you are interested in like hearing more possibilities, I released an EP using just Medusa's synthesizer engine to show how many possibilities there are for this. So that essentially closes our talk for today. I hope I would have more time to explain how all of this combines. Like, if you are interested in this, you probably want to invest more time to make the sound better by decreasing aliasing with replacing our nearest neighbor hopping algorithm with some better one. You might use Python to achieve some better performance. In fact, I will be talking about this very subject at Montreal Python later this month. And you can make our envelope more complex. Like, we only use the simple AD envelope, but you might just as well use a full ADSR, meaning attack, decay, sustain, release, even with exponential slopes, which sound more natural. The code is available on GitHub, so don't hesitate to ask me for details if you didn't understand a particular bit here. Thanks for watching. See you next time.